But these holomorphic transformations will actually still have some algebraic flavor. So I hope it's not too far away from algebraic geometry. Okay, and feel free to interrupt me at any time if you have some questions, okay? So let me start with some historical comments. This is the Markov equation, x squared plus y squared plus z squared equals 3 times x, y, z. And the Diophantine positive solutions are called Markov triples, and then any coordinate of a Markov triple is called a Markov number. And what is very easy to see is that 1, 1, 1 is obviously a solution of this equation. And because the equation is completely symmetric, any permutation of a solution is also a solution. And then there is another transformation. We keep x and y fixed, and we map z to 3xy minus z. And it's easy to check that this again maps solutions of the equations to solutions of the equation. And of course, it maps integers to integers. And if you think of this equation as an equation in z, when you keep x and y fixed, it's a quadratic equation, so it has only 2 solutions. Therefore, it must be an involution because it has no other choice to map back and forth these 2 solutions of a quadratic equation. And Markov, he actually did a lot of more things with this equation, but in particular, he showed that all positive Diophantine solutions can be obtained in this way. So, and there is a way to organize this in a tree, which is nowadays called the Markov tree. So you start with the solution 1, 1, 1. Then you apply this involution. You get 1, 1, 2. Of course, if you apply the involution again, you just go back. So what we can do now is we can permute it, right? We can look at 2, 1, 1 and 1, 2, 1. And if we take one of those and let's say 1, 2, 1, and apply the involution again, we arrive at 1, 2, 5. And then we can do this again. Now we have these 2 permutations, 2, 5, 1 or 1, 5, 2. We apply this involution. We get to 2 different new solutions. And from now on, it will be a binary tree. So you can always get 2 new solutions from here. So this is how this tree will look like. And now let's also look at the Markov numbers. So if you just go through this tree, we have 1, 2, 5, 13, 29, 34. And now the next Markov number is 89, but you don't see it. So we have to go deeper in the tree. Then we have this one, this one, this one. And there's again a number deeper in the tree. And then 433. So you see the growth of Markov numbers is not completely obvious. When you just go deeper in the tree, you might miss some of the smaller numbers, right? So as you see for the examples of 89 and 233. And people have investigated this from the viewpoint of Diophantine equations for a long time. So first important conjecture is due to Frobenius. And he considers ordered Markov triples. I mean, since you can always permute them, we just require that x is less than y and y is less than z. And he conjectured that it's uniquely determined by the biggest value, by z. And this is still an open conjecture. So what we know, for example, if we fix z, then there exist only finitely many ordered Markov triples. If z is the power of a prime number, there is exactly, I mean, there's at most 1 ordered Markov triple. I mean, only if z, of course, is a Markov number. And there is a whole book about this, Markov theorems and 100 years of the uniqueness conjecture, which contains a lot of interesting results if you are interested in these Diophantine equations. And I mentioned the growth of Markov numbers. So there is another conjecture from Don Zaghir, and he came up with this growth estimate. And he actually proved a weaker version of this, where he had some bigger growth than O of 1, small O of 1. So for small O of 1, it's just conjectured as far as I know. But in any case, even if you allow slightly bigger bounds here, then it's actually known that the growth looks like this. So I mentioned these two things because I will revisit these later again in the talk. There's a lot more to say about Markov surfaces. There's a lot more connections, but for the purpose of this talk, I have to limit myself a bit. Okay, so now I'm leaving the area of Diophantine equations and move on to algebraic geometry. So we can consider this surface over the complex numbers. And here I drew a real picture of it. What you can more or less guess from the picture is there's a singularity of type A1 in the origin. Of course, you can also get it directly from the defining equation. And it's simply connected. At least it does not contradict the picture, but one can prove that it is simply connected. Of course, if you remove the singularity, the surface will no longer be simply connected. So it's important that the singularity is part of the surface. Okay, I'm just going to rotate it a little bit. So here you can see also the Markov triples, the first three. I show these points here on the surface. And now there are a few results. So there is a description of, well, it's not a description of the automorphism group, but there's a description of how some group acts going back to El Houthi, but it was the paper by Sasha Perapechko where the automorphism group was actually precisely identified, as far as I understand. And what we have the permutations, we have this involution, and then we can flip two signs of the coordinates. And these together, they generate the automorphism group. And so you see here the group, it's PGL2 over the integers, semi-direct product with the Klein 4 group. And in particular, it's a countably infinite discrete group. And we can also rephrase Markov's result. We can say the group of polynomial automorphisms acts transitively on the Markov triples. Well, if we allow for negative coordinates, right, then we just add them and then we act transitively on this set. And now we're going to move to the holomorphic situation where things are a bit different. So we first start right away with some computation, but the computation is relatively easy. So let's say you want to write down a vector field that is tangent to the surface. And then one of the simplest vector fields that you can write down, if it's not the zero vector field, is this one here. No z derivative, only x and y derivative, with these linear quadratic terms here. And the claim is this one is tangential and has complete flow. Tangential is very easy. I mean, you look at the one form n, whose kernel is the tangent space, and you just take what is in front of the dx and put it in front of the partial derivative dy, and same for the other with the minus, then you immediately get that this is tangential, right? And now we have to compute the flow. And I'm saying this flow is complete. That means the flow time exists for all complex numbers. Okay, so if we look at this equation, z is not changing. So we have this system of equations, which is actually, if you fix z, a linear system. So you can just use first year math to find the solution. And here is the solution. All right, so I can write it using some sine and some cosine. And now the important thing to notice is that this is actually holomorphic also in z, right? Because here we have a cosine with the square root. And now, of course, you can say, well, but the square root is not well defined. There are two choices. But the cosine, if you develop it as a power series around 0, has only even powers. So this ambiguity in the square root will cancel out. Same goes for the sign. It has only odd powers, and then we divide by the square root. So again, it cancels out. So we have this defined for all x, y, and z, and all times t holomorphically. And now we have already an uncountably big family of holomorphic automorphisms, right? Because for every fixed time t, the flow will be an automorphism. So we have already found a lot more automorphisms than in the algebraic case. Okay, now we're gonna, first just, of course, the picture looks very boring. I tried to draw some flow lines here, and since the z coordinate is not changed, it just looks like parallel lines projected to the surface. But now, of course, because of the symmetry, we can play this game with all the other coordinates as well. I can just permute x, y, and z, and I get the vector field Vx, I get the vector field Vy, and they will also be complete and tangential. And then we notice, it's a very simple computation, that these vector fields span the tangent space, except in the origin, of course. And now I need some small lemma. It's of course in the context of algebraic geometry well known. If you have an LND and you have a function in the kernel of an LND, you multiply it with the LND, you get again an LND. But the thing is just true in general. If you start with a complete vector field and you multiply it with the function in the kernel, then it's again complete. And the proof is straightforward. You just take the flow map and you multiply with the function in the flow time. And because the function is in the kernel, it stays constant along flow lines. So it's like multiplication with the constant, basically. Okay, so we have this result. And now, of course, if you look at the vector field Vx, it's obvious that x, or actually any function of x, is in the kernel of this vector field Vx. Similarly, y is in the kernel of Vy, and z is in the kernel of Vz. So then we get that we have all these vector fields here, x to the k times Vx, and so on, and they are complete. So now we have already a huge collection of complete vector fields, and each of them comes with the one parameter family of holomorphic automorphisms. Okay, so that's a fundamental difference to the algebraic situation where we have an infinite but discrete group. Now, okay, there's one more thing. If you have a complex hypersurface, then it always admits a complex volume form in such a way that it can be extended to the standard volume form in the ambient space. What do I mean by extended? Well, I just illustrated here in this example. This is our Markov surface. This is the one form that defines the tangent space. And then I simply can write down this volume form on the hypersurface. And what I do is I just, if I have dx wedge dy, then there is one missing coordinate, the dz coordinate, and I just pick the coefficient here from n, write it here in the denominator. And so then, of course, you have these other ways to express it. And you see that this form is well defined, except if all three denominators vanish. And this is precisely the case in the singularity, right? And then you also see if you take omega wedge n, then you get the standard form back, because this is here the denominator, what's written here as the coefficient, so it just cancels out, right? So this is what I mean by extends to the standard volume form. And then, since we know all the generators of the polynomial automorphism group, it's just straightforward to check that polynomial automorphism will preserve this form up to a sign flip. I mean, depends if you have a transposition, then the sign will flip, but for the involution, the sign will stay the same, for example. Okay, so now I can state the two main results. Every holomorphic symplectic automorphism. Okay, I should say one thing. I'm going to use symplectic here instead of volume preserving, because it's the same for a surface, right? A symplectic form is a closed two form that is nowhere degenerate, and the volume form for a surface is also a closed two form that is nowhere degenerate, so it's the same. And it will be better to consider it as symplectic, as we will see later in the proof. So it's just a conceptual thing, but you can think of volume preserving if you prefer. And every holomorphic symplectic automorphism of the Markov surface that is path connected, C1 path connected to be precise, to the identity inside the automorphism group, can be approximated arbitrarily well by certain automorphisms that arise as flows from these three types of vector fields that we had before. So in some sense, they are the building blocks. They are not generators in a group theoretic sense, because we have to take limits, right? But let's say let's say if you consider it as a topological group where you are allowed to take limits, they will generate. And I'm just citing the algebraic case here again, so to see the large discrepancy between the discrete situation here and this extremely big group here. And to the best of my knowledge, this is the first example where we have an infinite but discrete algebraic automorphism group on one hand, and then on the other hand, an infinite dimensional group of holomorphic automorphisms. And then I mentioned before the theorem of Markov that we act transitively on the Markov triples. And now here we can actually do more. We can actually permute the Markov triples. So you can come up with any permutation of the Markov triples. I will do it only for the ordered ones, but you can permute them as you like. And then you will find an automorphism that does precisely what you wanted. So again, it's a case of transitivity versus infinite transitivity. Okay, I'm gonna start with the proof of the second statement because it needs less theory. So we can basically start right away and try to construct this automorphism. Okay, for that, I need to talk about something which is called tame sets. So, of course, in algebraic geometry, you know very well that the polynomial automorphisms on Cn, when the dimension is at least 2, they act m transitively for any m. So you can pick m points and move them wherever you want as long as they're pairwise disjoint. And then, of course, the situation in the holomorphic setting is a bit different. And the natural question is to ask, what about infinitely many points? And this was investigated by Rose and Rudin in 1988. And they call an infinite closed discrete subset tame if it can be mapped to the natural numbers that lie, say, on the first coordinate axis. And of course, this definition of tame only makes sense if not every set is tame. So they came up with the well, it's sort of constructive. It's a limit process, but it's in the sense of analysis, it's constructive way to show that there exists such a set which is not tame. And on the other hand, they also gave several criteria when a set is tame. And then there is another theorem by Winkelmann. He looks at a sequence without repetition. And then he says, if this series here is convergent, then the set that is formed by this series, by this sequence, is tame. So this is a sufficient condition, but it's not necessary. There are examples of tame sets that do not fulfill this condition. But nonetheless, it's a very practical theorem, and it gives you some intuition, right? A tame set should escape to infinity fast enough so that this series here is convergent. So now the question is, of course, how do we generalize this notion to manifolds, right? Because this is very specific for Cn. A tame set, well, it's a natural numbers lying on the coordinate axis. Well, so this is what I investigated together with Riccardo Ugolini. And there is also another competing definition by Winkelmann, but for interesting classes of examples, our two definitions agree. So what we came up with is the following. We say a set is tame if for every injective self-map of the set, there exists a holomorphic automorphism that does precisely what this self-map does when we restrict it to the set. And you see this right-hand side of the equivalence now makes sense in a manifold. I can just use this in a manifold as a definition. And it will agree with the original definition of Rose and Rudin because of this lemma. And now we can also extend it to the singular situation. So we look at normal reduced complex space, and we look at some set which is in the regular part of that space. And then we call it tame if we can interpolate any injective self-map of that set by an automorphism. And of course, we can also restrict this a little bit. For example, we could pick a smaller group than the whole automorphism group, right? We could ask tameness for just the symplectic automorphisms or the volume-preserving automorphisms or all automorphisms. Now we have this definition. And in general, it's not clear that tame set exists, right? Because you have to construct a set where this property is satisfied. But we did that for a large class of examples. For example, if you take a linear algebraic group and then a homogeneous space of a linear algebraic group, as long as the space has dimension 2, it will contain, at least dimension 2, it will contain a tame set. And then there is another theorem by Winkelmann, and he said, well, for every Stein manifold, there exists some bad set such that any automorphism on this set does not map the set to itself except for the identity. And of course, such a set cannot be tame because, for example, I could just permute 2 points, but then I will not find an automorphism that does it, right? Because of this property. So in general, there are plenty of sets which are not tame. And while the original difficulty of Rose and Rudin was to find a set that is not tame, now we know the situation is actually reversed, right? Most sets are not tame, and it's difficult to find a tame one. Okay, and of course, if I can prove that the ordered Markov triples are a tame set, then I will have proven the theorem that I can interpolate any permutation by an automorphism. Okay, so let's, before we start with the actual proof, just do some heuristics. We have the theorem of Winkelmann. Of course, it's true only for Cn, but still, I mean, let's take n equal 2, and let's take the growth conjecture by Zagir, plug it in there. Okay, this series looks reasonably convergent. So at least it's not a big no, right? So we can actually try to invest some work and see if we can prove the statement. Okay, so this is now the theorem. The Markov triples, the ordered Markov triples form a tame subset of the Markov surface. And we're going to construct it quite explicitly. So we have these 3 vector fields Vx, Vy, Vz that I introduced before. And we have their flows, phi x, phi y, and phi z. And given any injection from the natural numbers to the natural numbers, that tells me basically how I map the pairs, the triples to each other. I want to construct an automorphism. So the goal is I find some automorphism F, and I have here the jth Markov triples, so xj, yj, and zj are the x, y, and z coordinates of the jth triple, and I wanted to map it to the triple I of j, right? So, and I intend to construct F in the following way. I use here phi y and phi x, and I conjugate it by phi z. And what I do here is I take these flows And we already know that, for example, for yz, f of z is in the kernel. So this will also be a complete flow, and then I just choose the flow time to be equal to 1. Right? So this is what we have seen in one of the slides before. And this is how we're going to construct it. Now, just recall that this formula for phi z looked like this. And so we have a small issue with moving points wherever we want if this square root is 0, right? Because if the square root here is 0 inside the cosine, then the cosine just becomes a constant function, and I cannot, choose really anything. And no matter what kind of t I choose, I cannot really influence what the coordinate will do, and the similar problem happens with the sine function. So now I'm just going to illustrate the proof on the next slide. So I have to remove this bad set. So what I'm going to do, I remove the set with, so this is in the xy plane. And so you should think of the Markov surface being a two-sheeted branched covering over the xy plane because it's a quadratic equation in z. And I remove this set where z is equal to 0. Just because the singularity has this coordinate, this set coordinate, and I remove the set where the argument in the cosine or the sine would be 0. And it just turns out when you do the computation that you get 2 lines, and it's two-sheeted, so you get 4 lines. So this is the picture, and the blue and the black lines are lines that we want to avoid. Of course, this is just a real picture, so the complement of these lines is, of course, connected. So what we're going to do now, here we have these Markov triples. I just drew the first few ones. And the proof is true over in a more general setting, but I'm just going to assume as a simplification to make the proof easier that the uniqueness conjecture holds. It's not necessary, but it makes it easier for the sake of this presentation. And then each ordered Markov triple is determined by the last coordinate. So now I'm going to choose for each point zj a flow time tj such that phi z tj has the property that if I look at this for all, for each, I'm going to choose a time tj, but then I'm comparing the results, and I want that all the x coordinates are pairwise different, all the y coordinates are pairwise different, and that no accumulation happens. And once I have found this time tj, I simply pick a holomorphic function. I can use Weierstrass or Mittag-Leffler theorems to find them, and I will get a function such that f of zj is equal to tj. And then I just plug this function in here. It's still an automorphism, as we have seen, and it will do exactly what we want. So now I move these points here, because here I have some problems, right? Here, for example, the x-coordinate is the same for these 3 points that we can see here. Now this is done. This is solved. And now I use the same reasoning. I apply phi y. Phi y keeps the y-coordinate fixed, so I can adjust the x-coordinate. So I just move all the points to the new x-coordinates that I want to have. And then in the end, I use phi x to adjust the y-coordinate and move them to the new points. And then in the end, I conjugate back with phi z, and then all the points will go to the original Markov triples, but they have now been permuted accordingly. There is, of course, some tiny detail that we have to take care of. The set coordinate also needs to be correct because it's a two-sheeted covering. So in principle, I could end up with the wrong set coordinates, but some extra care will solve this issue. Yeah. So this proves the theorem. So we have shown that the ordered Markov triples are a tame subset. Okay, now I want to go back to the proof of the first theorem about the automorphisms, but here we need a little bit more theory. Okay, just let me very quickly look at the notion of symplectic and Hamiltonian vector fields. If we have a symplectic form, and then we call a vector field symplectic if the Lie derivative of the symplectic form with respect to the vector field vanishes. Then we can use Cartan's homotopy formula, and because omega is closed, this term here vanishes, the second one, and it just means that the inner product of omega with the vector field is a closed form. And then we can ask for a little bit more, namely if this form is not just closed, but exact. In that case, it means it's the derivative of a function. And then we call this Hamiltonian vector field, and obviously because every exact form is closed, every Hamiltonian vector field is symplectic. And now the surprise is that, for example, the vector field Vz that we studied before is actually a Hamiltonian vector field, and the Hamiltonian function is z. So of course that's why I named it Vz, because it's really the vector field of the Hamiltonian function z. And if you have zk times Vz, then you just have to take z to the power k plus 1 and divide by some constant. Then you get this. So these vector fields that we have investigated so far, they are all Hamiltonian vector fields. In particular, they preserve the symplectic form. Okay, now, so very, very briefly, vector fields form a Lie algebra. We have the commutator that gives us the Lie bracket. And it's easy to check that the symplectic vector fields form a Lie subalgebra, and also the Hamiltonian vector fields form a Lie subalgebra. And in fact, for Hamiltonian vector fields, we can say more. So if VV is the Hamiltonian vector field of the function f, and W is the Hamiltonian vector field of the function g, and then we ask what is the Hamiltonian function of the the commutator between V and W, then there is a way to express this, and this is called the Poisson bracket. And of course, since we have these defining properties here for a Lie algebra, the Poisson bracket must satisfy these properties as well. But we get some bonus, namely the Poisson bracket also satisfies the Leibniz rule. So it is much easier to work with the Poisson bracket in the case of Hamiltonian vector fields than to actually compute commutators. Okay, now why would we even care about the Lie algebra structure? What does this have to do with automorphisms? Well, this is, okay, will be the next slide. First, I have to tell you how to compute the Poisson bracket. And there is, again, a general rule to do this. So if you look at our symplectic form here on the Markov surface, then you can actually compute the Poisson bracket between x and y, and it will be minus what's written here in the denominator under the dx wedge dy. So that means if you have the symplectic form, you can basically read off the Poisson brackets. And then by bilinearity and the Leibniz rule, we know the Poisson bracket for all polynomial functions, right? So that's very useful. Okay, now I have to tell you why we actually are interested in this Lie algebra structure. And so we start with two vector fields, and we know their flows. And then there is a formula how to compute the flow of the sum of these two vector fields. So we simply compose the flows, but then we divide the flow times by k, and then we iterate this k times the composition. And then we take the limit k to infinity. And this will converge to the flow. If we are in the context of complex analysis, it will converge locally uniformly, and it will converge exactly where the flow exists. And then we have the same statement for the commutator of two vector fields. The formula is a bit more complicated. We have to take some square roots here. And in order to make sense of the square roots, the time should be positive. This is, however, not an issue because if you have some complex or negative time, you can just rescale the vector field with the constant and then just use positive time instead. So this is not really a restriction. So I think this is probably known since more than 50 years. But then it was Varolin in the year 2000 who made this crucial observations. Namely, if you have some Lie algebra generated by some set of vector fields, then you can use this to approximate every flow of a vector field from that Lie algebra by compositions of flows from these vector fields, from the generators. And then he came up with the following definition, namely, we take the closure of this Lie algebra. We are in the context of complex analysis, so it's again closure with respect to the topology of locally uniform convergence. And we say it has the density property if we can choose these generating vector fields to be complete vector fields. And why is this definition so important? Well, it means you can pick any vector field in this Lie algebra, look at its flow, which is probably not complete, but you can approximate the flow by compositions of flows of complete vector fields, which means you can, if you fix the flow time, then you can approximate this map, this flow, where it exists, by globally defined automorphisms. So that is a very useful tool, and that's our goal now, to prove this property in this context here for Markov surfaces. Okay. First thing, we're going to prove every polynomial Hamiltonian vector field with a polynomial Hamiltonian is in the Lie algebra generated by the Hamiltonian functions x to the k, y to the k, and z to the k, where k is any natural number. I'm not going to go through the proof in any detail. It's actually a quite tricky sequence of inductions, but let's do one step to just get a flavor of it for it. And this is the easiest step. Let's say I would like to get x to the k times y and all these other monomials here. Then, well, you just take x, Poisson bracketed x to the ky, use the Leibniz rule, and you get here x to the k plus 1y. This is the term that we want, right? But if we do induction in k. And we have another term that we don't want, x to the k times z. But if we assume by induction that all these terms were already there up to order k, then I can subtract it and I get this new term. And then, of course, I have to do this all together. And for example, I need to know that for the next step, also the term x to the k plus 1 times z will appear, so I can subtract it in the next step, and so on. But so this is the easy induction, basically. And then a bit more work is if we have x to the k times a quadratic term. And then finally, we want x to the k and y to the m, and x to the k and y to the m minus 1 times z. And when we're there, we're done, because we can always use the defining equation of the Markov surface to get rid of some more complicated terms. So not every polynomial we have to explicitly find, because we can use the Markov equation as an identity when we look at functions on the Markov surface. So this is just to get the flavor. It's like maybe 3-4 pages of computations, but then we get every Hamiltonian vector field is in this Lie algebra, which means we can approximate the flow of every Hamiltonian vector field by the flows of complete ones, by this previous lemma and corollary. Okay, but we want to talk about symplectic vector fields, not about Hamiltonian vector fields. So we need to understand that every symplectic vector field is actually Hamiltonian. And first, I thought that this is trivial because the surface is simply connected. And if you have a simply connected surface, you would expect that, well, every closed form is exact. And therefore, every symplectic vector field should be Hamiltonian. But there is a problem here, because what is a symplectic vector field? So there's a typo here. It should be a symplectic vector field. And, well, we plug it into this form, it take the inner product, and then takes the exterior derivative, and we ask this is 0. But of course, this whole computation only makes sense on the regular part of the surface. And of course, in the singularity, we want the vector field to be 0 because an isolated point, we cannot move this point anyway. But now the problem is that this form here is not defined on the whole surface. So I cannot just use any statements about forms on the surface. Of course, we could also try to remove the point. But if we remove the singularity, then the surface is no longer simply connected and also no longer affine or Stein. So we have to actually do some more work. So luckily, a long time ago by Grauert and Kerner, the notion of sheaves and differentials have been studied. They looked at like tangent sheaves and convinced themselves that they are coherent and so on in a singular situation. And then the next ingredient is that we need a Poincare lemma. And the Poincare lemma, a holomorphic Poincare lemma says, okay, locally closed form is exact. But in the case of singularities, this is almost always wrong. Okay, so Reifen gave very explicit counterexamples where you can see that this holomorphic Poincare lemma fails. But he also gave positive statements where you can actually verify if you have singularities of a certain type, then the Poincare lemma might hold. And then later there was a paper by Saito who showed that if your singularity are given by a quasi-homogeneous polynomial, then the holomorphic Poincare lemma holds. And this is precisely the case for our Markov surface. So, okay, Poincare lemma holds. Then we can use the standard argument from sheaf cohomology, and we get that the first group of the holomorphic de Rham cohomology is isomorphic to the first cohomology group with coefficients in the complex numbers, and this is trivial because it's simply connected. So then this works. But now we still have the problem here, right? Now we know, okay, everything works, but we still have our form not defined in the singularity. So one has to look at this more carefully. And it turns out if you have only very nice singularities, the so-called ADE singularities, then if the form is closed, it will actually extend. So the form is closed on the regular part. If that's true, then the form without the D is actually defined also on the singular part. And then we can apply the whole machinery and we say, okay, holomorphic, the holomorphic de Rham cohomology is trivial, so this closed form is actually exact. And therefore we get that the symplectic vector field is Hamiltonian. So this requires a bit more work than one would initially assume. Okay, so now we have to do some analysis part. I mean, there was some analysis before, but this is now really the analysis part where there's nothing really algebraic in it. This theorem is called the Anderson-Lambert theorem. And it was proved by Anderson-Lambert for star-shaped domains in Cn. Then it was proved by Forstnich and Rosé, also in Cn, for Runge domains. Domain is called Runge if any holomorphic function on that domain can be approximated by a globally defined holomorphic function uniformly on compacts of the domain. You know, of course, from one variable complex analysis, there's a very nice topological characterization of Runge sets in one variable. Unfortunately, in higher dimensions, this completely breaks down. So we simply call a domain Runge if this property holds, that we have this approximation property for functions. And then Varolin generalized it to manifolds, Stein manifolds with the density property. Then there was a paper by Kucherbauch, Leuenberger, and Liendo who generalized it to singular spaces, not just manifolds. But they could only do this for holomorphic automorphisms of singular spaces. So they couldn't handle the symplectic form or the volume form. And this is precisely for what I explained in the previous slide. For the notion of symplectic vector fields on a singular space, you have to work more, right? There is this piece was somehow missing from the previous slide. And so now we have this theorem also for singular spaces as long as the singularities are of type ADE. And this is some sort of Runge approximation theorem for holomorphic injections. So let me give some small pictures. So we have some domain omega. I fix a compact in this domain. And with respect to symmetric, I fix an epsilon. And then I have some holomorphic injection, which in our case also should be symplectic, which starts at the identity and moves it somewhere and deforms it. And through the whole deformation process, we ask that it's always Runge. And then I want on this compact here to find an automorphism, so globally defined, that basically does the same as this phi1 on the compact, up to a deviation of epsilon. And this is what the theorem gives me. So on this compact, I will be close. If I go to the boundary of the domain, of course, it will be horrible. But on the compact, which I can choose as large as I want inside the domain, I can get this approximation. And moreover, we know how these automorphisms will look like. Namely, we can take them as flows of complete generators from this dense Lie subalgebra that we used in the notion of density property. Okay, so I see that I have only 10 minutes left. So I think I will skip the proof of this theorem. Just what I want to mention is the following. If I now take omega, this domain, to be the whole space, so omega equals m, and I simply take an automorphism that I can connect to the identity, then this phi t will simply be a family of automorphisms connecting the automorphism to the identity. And then it will tell me that this automorphism that I started with can be approximated by flows of complete generators of this dense Lie subalgebra. So it means I will get an approximation result for the automorphism. And I will know, okay, if I know the generators of this Lie subalgebra, I know I can write any automorphism as a limit of compositions of those, as long as the automorphism is in the identity component. Okay, so I'm going to skip the proof. And go back to the theorem that I wanted to prove. So just to recall the steps, we had every symplectic vector field is Hamiltonian. And every Hamiltonian vector field is in this Lie algebra generated by the Hamiltonian functions x to the k, y to the k, and z to the k. So we can approximate every Hamiltonian vector field by the flows. And then we use the theorem, the Anderson-Lambert theorem from the previous slide, applying it to an automorphism, and we choose omega equals m, as I explained. And then we get this result that the flows of these Hamiltonian vector fields with Hamiltonian x to the k, y to the k, z to the k approximate any automorphism that is connected to the identity. Okay, so this proves this theorem here. And so I now want to just say a few words about the generalization, because in the title of the talk it said Markov surfaces in the plural, not just Markov surface. So what we can do is we can take this equation, x squared plus y squared plus z squared equals 3 times x, y, z, and then we can add an affine linear term. So we have some parameters a, b, c, and d. You can always normalize the parameter e to, let's say, 3 or 1 or whatever you prefer, and change the coordinates accordingly. But for the examples here, it's just easier if I'm allowed to vary e as well. So if I choose ABCD equals 0 and e equals 3, we get our original Markov surface with the type A1 singularity. If I make some special choices here for these parameters, I can get a singularity of type A3. There's also one special configuration where I can get singularity of type D4. And there is another configuration where I get 4 times the singularity A1. And that's precisely a fine form of the Cayley cubic, right? I mean, the Cayley cubic is known to be the only one, I think, with 4 times an A1 singularity, and this is just an affine version of it. And then the good thing is that every Markov-type surface has only isolated ADE singularities and is simply connected. This is a result that is in the paper of Quentin and Loret. They did a lot more in their paper. They have a lot of interesting results about Markov surfaces that I didn't touch at all now in my talk, but for me, for my application here, this was like extremely important that we know the singularities are mild and it's simply connected. And then by the same strategy of proof, I can extend both theorems to any Markov-type surface. So we have this approximation result for the automorphisms. And then, of course, if you look at this general Markov surface, there is no Markov triples here, because you cannot expect that there are any Diophantine solutions if you choose ABCD in any way that you like. But still, you can adopt the same construction that I had in the proof to show that they contain a tame subset. Okay, so I would like to conclude my talk here, and thank you very much.
Thank you, Rafael, very much. So, are there any questions or remarks?
So I have a question. You consider in the way of, so you consider the Lie algebra generated by this Hamiltonian, let's say, functions, yes?
Yes.
So is this Lie algebra simple?
You mean, that's a question. It's a good question. I don't know. In the holomorphic setting, I guess it's not. I mean, if you take the limits and you want to look at the holomorphic situation, I think it's not simple. If you look at the algebraic situation, I mean, what do we get? The Lie algebra that we get is the Lie algebra on the level of Hamiltonian functions. We just get the algebra of regular functions on the surface, right? We get all of them. So the question is simply if the Lie algebra of all polynomial vector fields is simple. I do not know in that particular case.
Of
So
all,
I mean that the symplectic form does not restrict your algebra from all.
you mean of all volume preserving, I guess, no?
So yes, it's volume preserving. Yes. Sorry. Yeah.
Sure,
Sorry.
yeah.
So you don't get all vector fields. You get all symplectic vector fields.
Yeah.
I do not know in the algebraic category if it is simple or not. In the holomorphic case, I think it is not simple if you take all of them.
Okay.
Because well, even in one dimension, we have counterexamples.
Okay. Thank you.
More questions?
Sorry, have you some information about arithmetic properties of Markov-type surfaces? When three, not with coefficient 3, with another coefficient.
No, I don't. But there are some of these Markov surfaces with some very special choice of coefficients are called, or the equation is called Mordell equation, because Mordell has studied some of these equations. I think in that case he chose, so ABC is 0, E is 2 or minus 2, and D is a natural number. And so there is a paper by Mordell where he studies it from that viewpoint. But apart from this special case, which is called Mordell equation, I don't know any further arithmetic properties.
Thank you.
Is it true that number of integer solution is infinite?
You mean if you choose A, B, C, D to be integers, arbitrary integers?
No, for example, for E equal to ABC D 0, for example.
I don't know, but I don't know if it depends on the n. I mean, D was n, a natural number in the Mordell equation. So one would have to check the paper of Mordell. I'm sure he wrote something about it, but I don't know the results in detail.
Thank you.
Ivan?
Okay, thank you, Rafael, for your excellent talk. But I have
Thank
two
you.
questions. First, about this theorem about approximation. So your results say that we can approximate any holomorphic automorphism by compositions of these complete flows, right?
Yes.
But do you have an example of automorphisms which is not composition itself, which needs this approximation? So maybe this...
Okay, so in this very special case of Markov surfaces, I do not have a concrete example. But in the case of C2, we have concrete examples. And so so what is the example? So okay, let's say you have variables x and y in C2, and you map to x times exponential of x times y, and the second coordinate is y times exponential of minus x times y. And you see that if you multiply the new coordinates, you get x times y, because the exponentials will cancel out. They have different signs. So it's easy to check that this is an automorphism. And this automorphism, this was shown in the paper already by Andrist and Lampert in 1992. This is an explicit example where you cannot write it as a finite composition, but you can write it as a limit of compositions. And the proof is tricky. So you need the Nevan-Linna theory about the growth of holomorphic or meromorphic functions to prove that you cannot do this. And surprisingly, it's the only example that we have, also in C2. But of course, there is a more abstract theory, which was also initiated by Andrist and Lampert in their paper. And they actually proved that there are many, I mean, actually, that most of them, in a certain sense, cannot be written as a finite composition. And this result can be extended to other manifolds. I did not extend it to Markov surfaces, but I'm very confident that it will also be true for Markov surfaces, that almost all automorphisms are just limits of compositions and cannot be written as finite compositions. But I'm not very optimistic that one can write down an explicit example.
I see. And maybe another question concerning your proof of this beautiful theorem that the collection of Markov triple form a tame subset in the surface. At the beginning, you mentioned this conjecture that this triple is uniquely defined by the last coordinates.
Okay, yes, let me go back to the slide.
Here it is. Maybe it's better to use the previous slide.
I'm here.
No, even next one.
Okay, should I go forward?
Forward. One more step forward.
More?
Okay, this was where you sketched the proof. Next one. Okay, so I will just say what I mean.
Okay.
You said that there is a conjecture which is still open, that this triple is uniquely defined by this last coordinate. And when you came to the proof of the statement about this tameness of such a collection, you said that for simplicity, you will assume that this conjecture is proved, but it doesn't influence or on the result, on the proof.
It does not. So the thing is, I mean, you know, I have a lot of freedom in these flow times. So making the projections to the coordinates pairwise different is not the problem. Even if we don't assume this conjecture, I may have to wiggle a little bit with other flows as well first. So the conjugation might be a bit more complicated, but the main issue is to avoid accumulation of the coordinates, because I mean, okay, if you go back here, okay, here these coordinates, they have all the same. These points have there are infinitely many number with the same x coordinate, and of course now the same happens for all the other coordinates as well. So if I do this for the z coordinate, and if I know that they are ordered and I have the z coordinate fixed, I know there are finitely many points only with the same set coordinates. This is known. And then I need to, moving these points will be fine. It will not cause any problem with accumulation. But the problem is later other points might by chance accumulate in the same place where I already had some of these finitely many points taken care of. So in order to fix that, I need a lemma that just picks the points or at least their coordinates, and moves them far away. So then there will be an additional step in the proof that first makes sure the points have different coordinates, and then I pick them and move them far away so that they don't interfere with the previous ones to make sure that there is no accumulation. So it just makes the proof more complicated, but it's still true.
Okay, thank you very much.
Okay, so further questions?
I have a question about tame subsets. You consider all injections in T cell. Is it enough to consider bijections only?
This is a very good question. So the short answer is I think it's an open question, even in CN. The point is the following. So, I mean, when we chose this definition and proved this lemma here, the first one, we had some concrete applications in mind. So, for example, of course, in CN, if you have two tame sets, they can be mapped onto each other because both are mapped to the natural numbers lying on the coordinate axis. But if you are in an arbitrary manifold, you would, okay, then of course you have no automorphisms. But let's say you have a nice manifold, like a homogeneous space of an linear algebraic group. And you have two tame sets in this manifold. And you would like to know that you can map one tame set to the other tame set by an automorphism. Because if you can't do that, then it feels very different from CN. And the way we chose our definition is actually to make sure we can construct this automorphism that maps one tame set to another. And if we replace here injective by bijective, we can no longer prove that statement. So it is kind of tailored to applications so that we can prove what we want. But even for C2, it's an open question if you can do it with bijective. So it's a good question, but I don't know the answer.
So if we take two definitions, so we don't know if we get the same subsets. So if there can be any difference.
Sorry,
Is
which
it possible
definition
that
do you mean? Is it on my side or is it frozen?
It is frozen. So something happened with connection.
Mhm. I
do
can
you
hear you.
me now?
Yes, now I
Yes.
can hear you.
The question is, if we take all subsets that satisfy condition on injective self maps, and we take subsets that satisfy conditions for bijective self map, do we obtain the same collection of subsets? So these definitions, as an example, that these definitions are not equivalent.
No, we have no. If you replace injective by bijective, I don't know any example where they are different. So they could be the same, but even for C2, it's not known if they are the same.
Yeah, thank you.
Okay, so do we still have questions? But then let me ask you a short question which is related to one of the previous one a little bit. So if you take this Markov-type surfaces, is there something known about algebraic automorphisms of them? So are they also infinite, for example, if you vary coefficients?
I mean, the automorphism group will always be discrete for these Markov-type surfaces.
Sure. But is it infinite?
And where is the result? What Sasha proved was, I think you had an extra additive constant here, right? You had like plus C. And for this plus C, which would be D in my case, the way I wrote was the constant D. I think you have the same result, right? That this is the group. But I have not found anything in the literature that would identify the automorphism group if we have arbitrary choice of A, B, and C. But maybe Sasha, maybe you know.
We have it, but it's not published yet. It was presented on some conference this summer. I can show you the table of automorphisms depending on A, B, C, D.
And also you can vary also 3. 3 can be changed.
3 doesn't matter. You can normalize it to whatever constant you want.
Right. You're right. You just replace X by CX or something. Yeah. Okay. This is stupid. Okay, but ABC.
Essentially, in PL2D, there is a subgroup of generated by involutions, this of index 6, and we have some finite extensions of this subgroup, depending on output parameters. We have a list
generated by involutions, but is PGL2? So maybe it's a stupid. No, nothing. No. Okay, I see.
Involutions generate a subgroup of index 6 in PGL2.
Yeah, okay.
It also, we can choose involutions in 2 ways, depending if we swap other 2 coordinates or not. So there is some caution, something. Okay. We can. I also wanted to ask, Rafael, you mentioned there are different singularities depending on parameters.
Yes.
Is there like complete list depending on parameters of singularities?
I haven't found a complete list, but okay, where are these things?
There is.
Sorry, that was too far. Okay, so what I can say from just looking at the equation a little bit more closely is that exceptional singularities do not occur. Okay, they could occur in principle, but they do not. Singularities of type dk only occur for D4.
Yes.
And there is
a list of
only one example where singularity D4 can occur. And all other singularities will be of type AK. And I do not know if A5 occurs, but for a cubic, A5 is the maximum. So we know we can already exclude most of the singularities, and then we just have a few. And I do not have not seen a list that would just say if you plug in A, B, C, and D, that tells you which singularity you have, except for D4. For D4, you have basically up to some rescaling or some isomorphism, only this one example.
Thank you.
Okay, so we had quite many questions.
Sorry, what about change power 2 on any power?
Okay, you mean for all x and y simultaneously? Same power?
Yes.
I do not know. However, I have started looking at some of these examples with higher powers. And what I can say is if all of the powers of x, y, and z are 3, then I don't find any holomorphic automorphisms with this method. That doesn't mean that there aren't any, but I don't find more than the algebraic ones. However, if we keep one of the powers a square and only increase some of the other powers of x and y, one can still find large groups of holomorphic automorphisms.
Thank you.
I mean, it's a work in progress. So maybe in half a year or so, I can give you a more detailed answer. But I'm looking at it right now. So it's a very natural question to ask.
Thank you.
Okay. Thank you very much, Rafael.
Thank
It
you.
was a nice talk, and thank you for actually agreeing to give it. Yeah.
Well, I
Anyhow.
would like to thank everyone in the audience for the interesting questions. I really enjoyed the interaction.
Thank you for a nice talk, really.
Thank you.
Yes, thank you very much.
Okay, see you in 1 month.
Our next
Bye.
meeting will be January 5. So we hope to see you on January 5.